There we go. Okay. So here we are. Today we're talking about polynomial behavior. Lots of different little aspects of polynomial behavior as we move toward a greater knowledge of polynomials, because so much is done with polynomials. So, there now. This is actually more of a piecewise defined graph, but it does the job. When we talk about increasing and decreasing and constant, which is the first part we're going to talk about here. We think in terms of left to right, like so much that we do in mathematics. So the hardest job for you, here's my tablet. The hardest job for you when we're talking about increasing, decreasing, and constant is to not pay attention to the arrows. Because right now, what we're doing for these topics, increasing, decreasing, and constant, we are moving left to right. Left to right. Left to right. Left to right. And of course, like always on the number line, left to right. Left to right. So as we move left to right, this side of the graph is going down. We call that decreasing. You know what decreasing is. Well, we're applying it to graphs. A flat graph is constant. So this part of the graph is constant. And this part of the graph, as you read from left to right, is going up, so it's increasing. And there's a mathematical definition of decreasing and increasing, but looking at a graph is usually enough to let you know what's going on if you remember left to right. Okay, so what we're going to do is just talk about the intervals of the x-axis on which the graph is increasing, decreasing, and constant. So let's do that right now. Let's let increasing be green. So I'm going to make this part of the arrow green. And the part of the x-axis that goes along with increasing is this part right here. Make it a little thicker. Okay, the interval of increase is read on the x-axis. Interval of increase is, if you were to say all of the words, it would be, what is the interval on the x-axis where the graph is going up? So let's see, this is 1, 2, 3, 4. Okay, so the interval of increase is for to infinity. Now, for those of you who are up on your intervals, you may be asking me, well, shouldn't it be like this? And the answer is no. We only use parentheses, and I'll tell you why when we're finished. That way you'll have a total view of this whole process. Now, decreasing is usually what's asked next, so I'm going to make that red. Actually, not red, because a lot of people can't see red. This is a mixture of red and blue together, so I think it will be visible. This is the part of the graph that's going down. That's decreasing. And the part of the x-axis that goes with this going from left to right, you've got negative infinity out here, and then going into, if this is -6, this is -5, this is -4 on the x-axis. So the interval of decrease or the interval on which the graph is decreasing would be negative infinity to -4. Now what's left? Constant. Let's make that blue. It's already blue, of course, but I'll go over it. The flat part is constant. And the flat part runs from -4 to +4. So right now I want to get my green marker and do that. Yeah. Now back to blue. Okay, so this is the part of the x-axis that we would say is the location of the constant graph. So the interval of constancy runs from -4 to +4. Now comes the reason we don't use brackets. It's because I cannot tell you whether here at -4, that's included in the decrease or it's included in the constant part of the graph. Which is it? If I have to use brackets, then this point right there on the x-axis can only be one or the other. It can't be both. So we have to make these points neutral. And we can do that by using parentheses instead of brackets. And that's the easy answer. I'm sure there's something much more complicated, but that's really what it comes down to. Okay. Now, ooh, this one's more complicated, but we have the same questions going on. Let's see. I'm going to do this left to right. Okay, a decrease in constant is blue, so let's make constant blue. Here's the constant part of the graph. We have a solid dot here. And then we have an open dot here. Well, with all of these closed and open dots, the whole story is allowed to change. And I can actually say that the interval on which the graph is constant is a bracket -10, -9, -8. -8 to -7, -6, -5, -4. This is -4 on the x-axis right here at this point. So from -8, and I can tell you absolutely that this is a point where the graph is constant. -4. All right, so I'm going to write the interval of constancy. Runs from -8 to -4. Great. Now increase is green. This from left to right is increasing. Okay, now I have a solid dot here, and I have a solid dot here. I can say with all honesty that this dot is part of the increasing and this dot is part of the increasing. So I am going to make my answers somewhere. Here, let me color this in first. Come down to the x-axis here. Okay, so the interval of increase. But it's increasing in another place. So we're going to have to study this situation, because note here that we have a point that's doing double duty. Is it part of increase or is it part of decrease? That's difficult. So let's come up here. Got to find out what these numbers are first. 1, 2, 3, 4, 5. And down here, 6, 7, 8. What I would say about this is that since we cannot declare whether that point is increasing or decrease, part of the increase or decrease, I'm going to put a parenthesis here and a bracket here, but I have to erase the 8. This is also a part of the increase. So I will have and this is -1 to -1 unioned up with 5 to 8. And then, yeah, oh, I didn't color this, so did I? See, there's fun in math. You get to color a lot if you want to. All right, now we're going to have decreasing, and decreasing I made that funny color. I think it's called dark violet. And here, the decreasing part is right here. Put a little dot in there too, which is that point. I don't know, I can't guarantee. So, the part of the x-axis that goes along with the decreasing part of the graph would be okay, this is x equals 0 right here. And this is x equals 5. So we're going to have 0 to 5. And 5 we can't guarantee. So the decreasing part I should have written an interval of decrease, but the decreasing part is going to go from 0 to 5. Now, that's the way it should be, but there's also an argument that says that the end point, can it be said to be part of the increase when there is nothing increasing after this? So I have seen in some books where they insist on just using parentheses even in this context. So check out what my math lab says, and be aware if you go on to calculus, you might use a book that says something different. And be flexible. Like with life, right? Who thought there'd be a pandemic? You've got to adapt and survive to whatever your current circumstances are. And this may be the best thing that happened to all of us, the pandemic. We're kind of being forced to be very, very flexible in what we call normal. Okay, enough philosophizing. Let us go on to more polynomial behavior. We're going to talk about another topic now. Relative maximum points, relative minimum points, relative maximum values, and relative minimum values. And here we have them. Notice that this graph, switch to blue, this graph continues to go up forever. That's what that arrow means. And this graph continues to go down forever. And to the left, and to the right, forever and ever and ever. It doesn't stop there at the boundary of the grid. However, even though all of these points up here are higher than that point, in its own little neighborhood, this is the highest point. This is like coming up out of the ocean and you've got a hill and then you've got a valley and then you go up to really high mountains. So this is the hill and it's higher, hilltop, and it's higher than the rest of the area around it, even though it's not the very highest point on the graph, any of these points would be higher. But that's why it's called a relative maximum point. So, -8, -1 is a relative maximum point. Now notice that the highest this gets, this goes down all the way to -50, so that is -1 on the y-axis. Notice that for all of the area where this is a relative maximum point, -1 is the very highest that this gets to. Every other place around it is lower. So -1, the y coordinate, -1 is the relative maximum value. Excuse me, I think my cat has a bird I need to rescue. What are you doing? This is my life. I'm not sure that there's a bird. I don't see a bird. She may just be playing. I hope so. She's certainly not hungry. All right, anyway, that's the story on relative maximum point and relative maximum value. Now we're going to look at the relative minimum point. In its area, this is the lowest point. You could make that, excuse me, you could make that area big or little, doesn't matter. But notice that all of these points are lower. So this is not the absolute lowest point on the graph, but in its own tiny little area, or not so tiny, it is the lowest point. It's the relative minimum point. So -2, -19 is the relative minimum point. Minimum, cheating. Minimum point, PT, point. And -19 is as low as the points in the neighborhood get. So negative 19 is the relative minimum value. And that's what there is to that. Here's another one. Here's a parabola. This is clearly not just a relative maximum point, it's an absolute relative. It's an absolute maximum point and a relative relative maximum point. Let me get a drink of coffee here. Okay, all right, I think I have it together now. This is the highest point, period, on the graph. The highest this gets is the y coordinate of the point, 3.25. So your book doesn't talk about absolute maxima, absolute minima. That's the plural. I don't know why. Because I'm telling you, that is the very, very highest point on this cup down parabola. So this is an absolute maximum point, and it's a relative maximum point. But keep my math lab happy, whatever you do. Negative 2.5, comma 3.25. And 3.25 is the absolute maximum value. There's no such thing as a math teacher. There is no math teacher on this planet that's completely happy with the book out of which he or she teaches, because nothing is perfect. All right, also, your book will say that's the relative maximum point. That's fine. The book is my math lab. My math lab is based on the book. So, yeah, this is the Beecher book, and it's a really good book as books go. I recommend you read it. It's more readable than most teachers. I don't know. This is the relative maximum point, just by virtue of being absolute. It's got no competition. And 3.25 is the relative maximum. Now, to be consistent, I should have made this Well, no. Yeah, I should have made it in green, but I didn't. Relative maximum value. Okay, now this question asks something else as well, and that is, what are the intervals of increase and decrease? So now I'm going to use green for increasing. Now you have to get that arrow out of your mind. And look at this totally from left to right. And when you do that, you see that that's increasing. I-N-C-R-E-A-S-I-N-G. And the part of the x-axis that is increasing with this is negative 2.5 here, because that says it is. And since this goes on forever, from negative infinity all the way in to negative 2.5, you've got increasing. So the interval of increase okay, similarly, and I'm going to use out and out red this time. From this point on the x-axis to the right forever, the graph is decreasing. So there you go, out to positive infinity. So the interval of decrease so there you go with that. Okay, now we're going to talk about something else. See, we've got all these little facts going on. So let's look at what part one dealt with: increasing, decreasing, constant, maxima and minima, that's plural. That's plural of maximum and minimum. Then we talked about relative maximum points and relative minimum points, and relative maximum values and relative minimum values, and the same here. And mixed it with increasing and decreasing. Notice that the relative maxima and minima are the points at which increasing becomes decreasing, or decreasing becomes increasing. For that reason, these are also called turning points. So many names. All right, now, this is so cool and so easy. There are two things you need to know and memorize. Only two. The graph of, and you know how I draw, so the drawing will be really bad. The graph of y equals x squared. Okay, that looks like this. And the graph, I'm going to come down here, the graph of y equals x to the third, which looks like that. That's my favorite graph. All right, well, why is that? Well, I'll tell you. You know that if you put a negative sign in front of the x squared, you get a cup down parabola. This is a cupped up parabola. Okay, so y equals negative x squared is just tipped upside down. And you have that. And the graph of negative x to the third is just this graph tipped upside down so that it looks something like that. Relatively. Just keep, actually it's these two graphs, but if you like, these four graphs in mind, because everything that we're about to do is based on that. It's unbelievable to me. This is both easy, well, it is easy. You can actually do things with your arms like, oh, it won't show up. My arms disappear when I raise them. It's very disconcerting to see your arms disappear. That's a problem with being online. Not only does part of you disappear, but you can't do all the motions you could do in a classroom. You know, the sillier things. I'll find a way to be silly anyway. All right. The leading term is the highest degree term. You know that. We've talked about it. Leading term. In this case, right here, the leading term is negative the square root of 11, x to the third. Okay. This, on the ends out at negative infinity, and out at positive infinity. These drawings are called end behavior. Negative infinity, positive infinity. For those who wonder what's happening way, 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 way out on the left and way out on the right on the x-axis. I mean, what is the graph doing way out at the extremes? Because we never bothered to graph that. Negative infinity, positive infinity, and negative infinity, positive infinity. Well, it just so happens that none of these other terms matter at all to what's going on way out at the ends. All that matters is the leading term. And in fact, the part of the leading term, the parts of the leading term that control all of the end behavior is whether the leading term is positive or negative, and is the degree even or odd. That's all you have to look at. We could go through here and just mark out all the other terms. They don't count. Except, look what they did here. They tried to trick us. I was going to mark out everything but the x to the fourth term. Look at that. That's the degree right there. That's the highest degree term, so we can mark out all the rest. Now, all of it's important, but not when you're dealing with end behavior. All that's important is the leading term, whether it's positive or negative, and whether the degree is even or odd. That's all that matters. That is so cool. And what does that have to do with this over here that I drew, attempted to draw? You'll see. Because way out at the ends, this leading term is going to cause the graph to look like this. It'll go up on the left and down on the right. It will look just like negative x to the third. Now this would be true if that were any odd number. So x to the fifth, x to the seventh, x to the ninth, x to the 11th, any number that 2 will not go evenly into is an odd number. And when it's negative, it's going to look like this. So B is what this graph is going to look like way out at negative infinity and positive infinity. It'll go up on the left, down on the right, just like y equals negative x to the third. Forget the middle part and just look at the ends. Because that's all we're talking about here. We're not talking about what happens in the middle. We're talking about what happens at the ends. Okay, so we'll look here. Here's the leading term, the highest degree term. This term, the leading term, the LT, is negative and of even degree. It's going to look like negative x squared. Y equals negative x squared, not in the middle maybe, but out at the ends. It's going to go down on the left and down on the right. And this is all I need to know about the leading term. So I would choose A. Notice the middle is blank because we're not talking about the part of the graph in the middle. We're talking about at the ends. Now they tried to trick us here, but let's look at that leading term. This leading term is positive. The LT is positive. And it's of odd degree. Well, the odd degree means it's going to look on the ends like either x to the third or y equals x to the third or y equals negative x to the third. Since it's positive, it's going to look like y equals positive x to the third, which means it goes up on the right and down on the left, way out at the extremes. So up on the right and down on the left, just like y equals positive x to the third. So these are just the models you want to keep in mind. Even degree, negative and even degree, positive and odd degree, negative and odd degree. These are the models for what happens out at the ends. So we're going to choose this way out at negative infinity and way out at positive infinity. The graph is going to look like this. And finally, here's another positive odd degree. The LT is positive and of odd degree. Which means it's going to look just like the other one, positive and odd degree. It's going to go up on the right and down on the left, way out at the extremes. Perfect stuff to put on a flashcard. All you're going to need is 4 flashcards. You can even write it out in a little table. Okay, I'm going to use this area over in here. Darn, I should have left myself room for a table. All right, let's go down here. Do I have extra paper? Yes, I do. End behavior continued. Oh, continues. Well, it continues. Yeah. Okay. All right. If the LT, the leading term, end behavior. Okay. Positive, even degree. Way out at the ends, it'll go up on the left and up on the right. negative and even degree. Down on the left, down on the right, and this is like y equals x squared, and this is like y equals negative x squared. Now, if the leading term is positive and odd degree, it's going to go up on the right and down on the left, just like y equals x to the third. And if the leading term is negative and of odd degree, it'll be the opposite. It'll go up on the left, although we'd really call that decreasing, but this is another topic. Just think of it as up on the left, down on the right. Down on the right, just like y equals negative x to the third. And that's all you have to remember, those four things. I love it when it's easy. Okay. You're going to hear the word zero a lot, and we are not talking about the number zero. Well, we are sort of, but not directly. We're not talking about the number zero itself, not the number zero. A zero is something completely different. A zero is a number that makes f of x equals 0. So what these people are asking right here is 5 a 0 of f of x? This is what the question comes down to, is 5 a 0 of f of x? If it is, then f of 5, that is, you put a 5 in for all the x's, will equal 0. So it's handy to use a calculator for this. This is what I'm going to do. I'm going to take f of x and I'm going to put a 5 in for every x, so that I'll have 5 to the third minus 11, 5 squared. So I really should put these in parentheses. Plus 11, 5 times 5 plus 95. If it equals 0, then 5 is a 0 of f of x. Later we'll talk about, okay, it's a 0. What does it do? Why do I care? Yeah, it's important. But right now I'm getting out the calculator. I have to make a decision about this in 4 days. I have 4 days left. Do I want to purchase it or not? We'll see. Oh, that may have been that problem. All right, anyway, here we go. No, that won't work. Now, I find that out every class. I need to put it over here. And then I'll make it bigger so you can see. So, yeah. The parentheses are above the 8 and the 9 key, if you don't know. So parentheses, 5, parentheses, caret, cube, and then right arrow key to come down. Or if you've, yeah, you'll always have to do that. No, you won't, not if you have the older model. Minus 11, parentheses, 5, squared, plus 11, parentheses 5, plus 95. So there I have 5 to the third minus 11, 5 squared, plus 11 times 5, plus 95. Enter. Woo! It equals 0. Okay, let me make this bigger again. This is what I did. I put an X in for every 5. The truth is, of course, you don't really need parentheses to do that unless 5 is negative. If 5 is negative, you absolutely need to have parentheses around the negative 5. Substitute it. But of course, it wasn't negative, so I didn't really need the parentheses. It's still a very good idea to get in the habit. All right, now, here's another problem, and we're being asked, oh, and look, it's out of order too, but that's not important to this question. Still, it could be important to us, couldn't it? Me, could be important to me. So, I'm going to do this again. F of X equals negative, oh, no, it is right. Never mind. Instead, let me do this. Good opportunity. This is a 3 we're putting in there. So this is going to be X. It's not going to be X. It's going to be 3. And again, 3 is positive, so I can just say 3 to the 4th minus 6 times 3 to the 3rd plus 4 times 3 squared minus 8 times 3 minus 69. Okay, so yeah, 3 to the 4th minus 6 3 to the 3rd plus 4 3 squared minus 8 times 3 minus 69. Okay. Okay. We'll do it this way. And then I'll enlarge it. So 3 caret 4. Right arrow key minus 6 times 3 caret 3. Again, right arrow key to come down. Plus 4 times 3 caret 2. I didn't have to do that. There's a squared key. And I would have not had to come back down, but since I used the caret, I've got to hit the come down button. And then minus 8 times 3. Minus 69. Oh, that was a point, wasn't it? All I have to do is overwrite it. Minus 69. So double check, 3 to the 4th minus 6, 3 to the 3rd plus 4, 3 squared minus 8, 3 minus 69. Enter. Negative 138. That is not 0. No, it's not. Well, I guess that means that 3 is not a 0. Which is not 0. So no, 3 is not a 0 of f of x. It's a very nice number, but it's not a 0 of f of x. 3 is not a 0 of f of x. Okay. Well, now we have to find the zeros, and this is going to make more sense to you. So what if it's a 0 and it makes f of x equal 0? So what? Well, here's the so what. And even then, I haven't totally answered the question, why do we care? We won't get to that until next week. All right, I am going to factor by grouping. So f of x equals x to the 3rd minus 8x squared plus, parentheses, negative x plus 8, which means the number in front of the x is negative 1. Okay, now, that's a square. Okay, now, f of x, find the zeros. No, watch what I do. F of x is y, isn't it? I'm going to write it as y. That's a very good thing to do with this line. To remind myself that f of x is just y. And we're looking for zeros. And the zeros live on the x-axis. So I'll even write that out. Zeros live on the x-axis, where y equals 0 all the time. So to find the zeros, I've got to let y equal 0. Now I can go about my business of factoring. I'm going to factor out a GCF, that's going to be x squared, parentheses, x minus 8, and I can check myself. You always want to check yourself. X squared times x is x to the 3rd. X squared times minus 8 is minus 8x squared. So I did that right. Now, the slightly harder part. When you're leading term, the degree of this term is 1. Because there's an invisible 1 power there. The degree of a constant is always 0. So this is the highest degree term. And it's negative, which means my GCF has to be negative. So here we go. I'm going to work on this over here. Negative 1 times x plus. Now I have got to pull out a negative 1. I have to get a -1 from somewhere. +8 equals -8 times -1. Now I have a -1 in both terms. So I pull out the -1 to the front and then write the leftovers. X plus -8, which is exactly the same thing as -1 times x minus 8. So that's what I'm going to come back up here and write. -1 times x minus 8. I've always thought that's so tricky. Okay, 0 equals. Now x minus 8 is the GCF because it occurs on the left side of that plus sign and on the right side of that plus sign. So I am going to pull out x minus 8 as the GCF. And then the leftovers are x squared minus 1. X squared plus -1. They're the leftovers after x minus 8 gets pulled out. Now don't think you're done, because x squared minus 1 will factor by the difference of squares. So 0 equals x minus 8 times x plus 1 times x minus 1. Now what we do is this. When you have solved a higher order equation by factoring, and you've got a bunch of factors, you set each factor equal to 0 and solve for x in each one of them. X minus 8 equals 0. X plus 1 equals 0. X minus 1 equals 0. And then you solve. I add 8 to both sides, so I get x equals 8. I subtract 1 from both sides, so I'll get x equals -1. I add 1 to both sides, so I get x equals 1. These are my zeros. -1, 1, and 8, located here. -1, 1, and 8. Those are the zeros of f of x. You don't have to list them in order. I think my math lab will take them in any order. And you know, there's a blue box around the answer box, at least for a while in the beginning. Those are your zeros. Now notice each one occurs once. That's what multiplicity is. How many times does the 0 occur? Well, each one of these occurs once. So the multiplicity of -1 is 1. The multiplicity of 1 is 1. The multiplicity of 8 is 1. Because they each occur one time. Well, do they ever occur more than one time? Yeah. Yeah. Suppose we have x squared minus 2x plus 1. Well, 1 factors into -1 times -1, and if I take -1 and add it to -1, I get -2. So this factors into x minus 1 times x minus 1. And I've got to turn this into an equation so that x minus 1 equals 0. Oh, I'm moving too fast. X minus 1 equals 0. X minus 1 equals 0. X equals 1 and x equals
this one is hers.
1. How nice. I need to mute. Mute all. Yeah, that'll work. Okay. Now notice that x is a 0. If we call this f of x, and we set it equal to 0 and solved for x, there is 1 0 of f of x. There is 1 0 of f of x. But it occurs twice. I should say, and it occurs twice. So the multiplicity is 2. So you can have multiplicities of 2, 3, 4, 6, 7, 10 million. Now, we have reached the end of our time together. However, there's one more problem I want to do in which you have to find the zeros. And the trick to doing this problem is to use U substitution and then show you how to work this. So I am going to stay here and continue talking and add these two problems onto the end of this video, and you should find it later today in Module 8 because this is week 8. Okay, I will see you later. Have a good day. Here we have x to the 4th minus 6x squared plus 5. This is a quartic, okay? It's not a quadratic. It's not a cubic, it's a quartic. And this is one of those rare situations where you've still only got 3 terms, so it's a trinomial. And the leading degree is 2 times the middle degree. When we have that situation, I can use U substitution to temporarily turn this function into a quadratic. So I can use the methods that I already know, the factoring methods, or even the quadratic formula to solve it and find the zeros. Let's do that. I'm going to let U equal, let U equal x squared. Squared is going to equal x squared squared, which is x to the fourth. When you have a base raised to a power and raised to a power again, you multiply the two powers. Okay, so this enables me to let x to the fourth temporarily equal u squared. So I am going to have f of u equals u squared minus 6u plus 5. So that 0, because I'm looking for the zeros, 0 equals u squared minus 6u plus 5. And 5 equals 1 times 5, but it also equals negative 1 times negative 5. And negative 1 plus negative 5 equals negative 6. So I am going to use negative 1 and negative 5 to factor this. Notice there's a 1 in front of the u squared, so I can use the faster method of grouping here, which I like a lot. 0 equals boom, 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 boom. Put a u, put a u. Put a minus 1, put a minus 5. Ta-da! Double check. U times u is u squared. U times minus 5 is minus 5u. Negative 1 times u is negative 1u. Negative 1 times negative 5 is 5, which, if I check this, gives me u squared minus 5u minus 1u plus 5. Negative times negative is positive. So u squared minus 6u plus 5 gives me what I started with. So that means I factored correctly. Now I set each factor equal to 0 and solve for u. Which is a dangerous step because I'll think I'm done, and I'm not. I'm going to add 1 to both sides in order to isolate the u on the left. So u equals 1. And I'll add 5 to both sides to isolate the u on the left. Boom. U equals 5. But I'm not done, because we have to solve for x. We have to solve the original problem for x. So remember, and we wrote it right here, u equals x squared. So this is x squared equals 1. And this is x squared equals 5. Now to solve this, I need to use the square root principle. So here's the square root principle. If I have x squared equals 1, then to get x equals, I need to take the square root of both sides and put a plus or a minus in front of the radical that houses the 1. So x equals plus or minus, the square root of 1 is 1. So that means x will equal negative 1 or positive 1. Now we come over to x squared equals 5. I take the square root of both sides. The square root of x squared equals plus or minus the square root of 5. So x equals the square root of 5 is a run-on decimal. It's an irrational number. So you can't put it in your calculator and get anything that would be an exact answer, and we have to answer with an exact answer. So your answer is plus or minus the square root of 5, so that x equals negative the square root of 5, and x equals positive the square root of 5. Therefore, the zeros of f of x, bring this up a little bit, the zeros of f of x are, and you don't need to put them in order, you can if you want to, -1, 1, negative the square root of 5, the square root of 5. These are the zeros, and by the way, they have different names. These are called real because they're real numbers, real, rational, zeros. These are real because they're in the real number system, irrational zeros. Okay, now notice one more thing as I add to your education. The original f of x problem was x to the 4th. That's the highest degree. There are 4 answers, 4 zeros. Now up here, f of x is a 3rd degree polynomial. Notice it has 1, 2, 3 zeros. We're going to be talking more about that as well. Right now, today, we have one more problem to talk about. This one. We're being asked to find the zeros and their multiplicities, and I didn't find the multiplicities up here. Each one of these zeros occurred once. Therefore, they each have multiplicity 1. Multiplicity 1, multiplicity 1, multiplicity 1, multiplicity 1. Now, we are going to find the zeros and the multiplicities one more time, and this is a doozy. I'm going to write this out. I'm going to expand it. I'm going to write it out the way it really is. Of x equals x times x times x times x times x times x times x. Now I believe that's 7 zeros, right? 7 factors. 1, 2, 3, 4, 5, 6, 7. Yes, it is. Now, x minus 2 is squared, so we'll have times x minus 2 times x minus 2. X plus 6 occurs only once. X plus 6. Now to find the zeros, we set f of x equal to 0, and this is in factored form. We set each factor equal to 0. So I will have x equals 0, x equals 0, x equals 0. All the x's are separate factors. X equals 0, x equals 0. 1, 2, 3, 4, 5. Okay, x equals 0. I'm getting a little bored with this. X equals 0. Thank goodness. 1, 2, 3, 4, 5, 6, 7. Okay, now x minus 2 equals 0. X minus 2 equals 0. X plus 6 equals 0. All right, now I have to solve each of these for x, but these are already solved for x, these 7. Now this, I'm going to add 2 to both sides. So I'll get x equals 2. Same thing here, plus 2 plus 2. Those zero out, so I'll have x equals 2. And finally, over here, I will subtract 6 from both sides. 6 minus 6 is 0. X equals negative 6. Oh my goodness. There are 3 individual zeros to this problem. The zeros are, I better write that. The zeros are the number 0, the number 2, and the number negative 6. Again, you don't have to write them in order, although it would be really easy to do that. Now, 0 has multiplicity seven. 2 has multiplicity 2. 1, 2. 6 has multiplicity 1, because it only occurs once. Now notice that this 0, x equals 0, has multiplicity 7. X equals 2 has multiplicity 2, and x equals negative 6 has multiplicity 1. You can clearly do these a quicker way, and I leave that up to your creativity. But if you move too fast, you'll mess it up. So reason through it and do it when you see a homework problem like this. Work it through the long way first, until you get the idea. Okay, all of this is fairly easy stuff. It's just stuff to add to your flashcards to help you memorize it. Meanwhile, I'll be back next time. Be sure to contact me with questions if you have any. Bye-bye.